Hello and welcome. This is Chapter 7 video guide. Let's get it started now. This one is coming off of the Chapter 7a half chapter practice. That's kind of a mouthful, and it seems like you're saying the same thing a lot. Now, if you're looking at that sheet, it has a whopping 33 problems. We will do them all. I will be here all night for you. That being said, I don't literally want to be here all night and morning for you. So 33 problems is quite a bit. After the first few problems, I'm not going to be skimming through it. But if I can mentally come up with like a perfect square and extract it, I'm going to call it out. If you have trouble following along, please press pause and work through that part on your own. I think that's a crucial part about this. Starting these problems normally tends to be the biggest thing, and obviously closing as well, just making sure everything cleaned up right. Careless mistakes can be made. I'm going to run through some notes first, through the simplifying part, and then through some notes through solving radicals, and then some notes through the graphing, and then that'll be it. So this will either be super long or right on time. Okay, first thing I want to run down is simplification rules. Now this is just general stuff. If you see the word simplify instead of solving equations, I really want you to understand what that means when they say what it means we're asking to simplify something. First of all, it does not mean solving. Right? When we're solving for x, you're trying to find out what x equals with something. Like, oh, x equals whatever else. We're not trying to solve for an x value. An x might exist in it. It might not as well. But our goal is to try and figure out basically how to clean up the problem. So these are things that I didn't get this off a book. I didn't get this online. I wrote these out. So forgive me if I state them wrong, and especially forgive me if I'm leaving a lot of things out. But in order for an expression to qualify as simplified, it must meet the following criteria. First of all, like terms have to be combined, including irrational and imaginary numbers. So like terms being combined, if you have x plus 2 plus x, I'm not going to run through all these examples, but you get 2x plus 2, yada yada. But irrational numbers are just as important, and this is a property that I do not have written down anywhere. So let me write it out for you. A plus c, or root c, plus b root c equals a plus b root c. The idea is that there is a multiple of root c being provided for both of these. Here's an irrational number and you combining like terms. So if this said 2 root 3 plus 4 root 3, that would be 2 plus 4 root 3, which is 6 root 3. Same idea. Okay, polynomials are factored and or written in descending order of degree, including radical roots. Basically what that means is if they're asking you to factor it, okay, you're going to do it by, you're going to factor something. You find a common factor or factor a trinomial or something like that using the diamond. And then writing things in descending order. We don't write 2 plus x, we write x plus 2. This is x to the first power, this is x to the 0 power. Anything else like a square root, write it after. Square root of x. Okay? Denominators in fractions are void of the following, which means you do not have these things in denominators. Ones and zeros. Okay? We don't write 3 over 1, we just write 3, etc. We can't divide by 0. Common multiples with the numerator. In other words, reduce your fraction. Don't write 2 over 4. When they have a multiple of 2, write 1 over 2. Radicals, you must rationalize your denominators. Imaginary numbers, you must make your denominators real numbers. Leading negatives, and we'll run into a problem like that for sure. It's going to be number 9, by the way. Decimals and other fractions. You won't have fractions within fractions, I sure hope. Okay, perfect nth power multiples are extracted out of nth root radicals. So the example here is if you have the if you have the square root of like 9x squared, don't leave it like that. Take out the perfect squares that exist in there. For instance, the square root of 9 is 3. The square root of x squared is x, or the absolute value of x, really. On that note, we'll talk about how absolute values work with that. There does not exist any negative exponents. Make sure all your exponents are positive. There does not exist any negatives in square roots. Please convert to imaginary numbers, if so. And all I to the n values must be simplified. So if you have, or ones that don't end in 1, so if you have I squared, that's negative 1. If you have I cubed, that becomes negative I, etc. We aren't doing imaginaries here. Those are just examples of what must be simplified. Okay, those are rules of simplification. If they ask you to simplify, do those things. Don't leave those out. All right, here we go. I will. Oh, do I want this page right here? I'm actually going to jump to. Yeah, let's do this. So, in terms of simplification, we will do properties. Okay, here are properties and examples. A to the m times a to the n equals a to the m plus n. What that means is if you have a base, a value, and it's the same when you're multiplying this and this together. Doesn't matter what the exponents are. When you multiply these two, you keep the base and add the exponents. So, for example, 3 to the 1/2 plus 3 to the 3/2 is 3 to the 1/2 plus 3/2, which is 3 squared, which is 9. A to the m raised to the n, so an exponent raised to an exponent means you multiply the exponents. The reason being, you're multiplying a by this many, and then you're multiplying whatever's in here by this many, so you're multiplying it by that amount right there. And here's an example over here. I'm going to speed through these a little more. I want to do some problems here. You distribute an exponent with a product, okay, right here. So you distribute the m to the a and the b. Check that out over here. By the way, they're using a lot of fractions in these examples here. Notice how 9 to the 1/2 became 3. This is a property that's also not written here. I'll go ahead and do it for you. The nth root of a to the m is a to the m over n. So fraction exponents, 9 to the 1/2 is the same as the square root of 9 to the first power, which is 3. Okay. Now you don't have to do 9 to the first power first. You can do that second. You can also write this as, like this guy right here, you can also write as the nth root of a, all raised to the m power. Doesn't matter which order you do it, you'll still end up with the same result. So I could have done the square root of 9 first, then raise it to the first power, and I still would have gotten 3. Same with 4 to the 1/2 power, that's square root of 4, which is 2. Okay, a to the negative m, again, no negative exponents. That would equal 1 over a to the m, where a could not equal 0. On that note, you could also have 1 over a to the negative m, and that'll equal a to the m power. Okay, there's your example. This one is like this one right here. These have a really, no, I'm sorry, not that one. Like this top one up here, they have a really distinct tie-in. When you divide something with the same base, you keep the base and you subtract the exponents right here. Obviously, a can't be 0 because you can't divide by 0. And finally, last one here, distributing, it's like this one right here. Distributing your exponent with your fraction, it's a to the m over b to the m. Check out those examples, as you will. Okay, I'm going to do 4 examples first here. They only involve numbers, so you can get a good look at basically how I'm going to apply these. Okay, fractional exponents. Here we go. First thing I want to do when attacking this problem personally is I want to apply this property right here. A to the negative m equals 1 over a to the positive m. When in doubt, get your negatives out of the way immediately. So this is 1 over 27 to the 2/3 power. Notice I didn't do anything but that step first. Next up I might not know 27 to the 2/3 power, and we're not going to use calculators on this exam, so rewrite this. The cube root of 27 squared. Now, do I want to write the squared in here as to imply that I'm going to square 27 first? You can do that, no problem, but remember, no calculator. What I'd rather do is take the cube root first and then square it, especially when this is a perfect cube. The cube root of 27 is 3, and 3 squared is 9. So that's your answer there. Oh, you know what? This isn't your answer because this is 1 over that. So this is 1 over 3 squared, which is 1 over 9. Already losing my logic here. So here we go. Let me get rid of that. That is 1 over 9. Okay, 32 to the 3/5. Same idea here. I can do 32 cubed and then to the 5th power. I mean the 5th root. Or I can take the 5th root first and then cube it. When in doubt, get small numbers. That's kind of a motto we're going to go with here. And 2 cubed is 8. No 1 over 8 is just 8. Okay, 16 to the 3/2. Once again, here we go. That is the square root of 16, then cubed. Square root of 16 is 4. 4 cubed is, what is that, 64? And finally, off to the side here, negative 8 to the 4/3 power. This is negative 8. Notice it's wrapped in exponents. So everything I do, basically, if this said negative 8 to the 4th power alone, I would do negative 8 times negative 8 times negative 8 times negative 8. I wouldn't do one negative and then multiply 4/8 together. So this is the cube root of -8, which you can do to the 4th power. Let's use a different color. I'm running into this other stuff. Cube root of -8 is -2. Now this -2 is wrapped in exponents. Negative doesn't sit on the outside. -2 to the 4th power is positive 16. Okay, now I went out of order here. Notice this was 16, 17, 18, 19. These ones had numbers in them. I thought it was more important to do that there and then go to all the other ones with variables, and this is the good lead into all the other stuff. Okay, a couple more properties to show you just really quickly here. The nth root of a product is equal to the product of two nth roots right there. So you can split them up and you can join them, and there will be good use for both of those. Likewise, you can do the same thing with fractions. They work just as easily. And like I said, there's good benefits to both of them. You'll see both be shown in good form here. And then the other thing I wanted to throw out there, they're not in this problem set because you'll see why, but they don't exist in this problem set. And if you take the nth root of a value to the power of n, it just becomes that value. However, when n's an odd number, you have to make sure that you maintain the sign. For example, if I took the 5th root of -2 to the 5th power, okay, notice how these are two odd numbers. These are your n's. -2 to the 5th power is -32. The 5th root of -32 is -2. Notice how that number stayed negative, just like when my x was negative originally. However, let's do -2 now to the 4th power and the 4th root of that. -2 to the 4th power is positive 16, and the 4th root of positive 16 is positive 2. Notice how when my x was a positive number before, or a negative number before, my result ended up becoming positive. So even when I use a negative number, I need to make sure that because this number is positive, that my value out here ends up being positive. So I have to make sure this is the absolute value of -2 when my n value is even. And that's a very important concept to have with you, because when you square numbers or raise them to the 4th power or 6th power, they become positive. But in these scenarios, this won't be the case. I just wanted to throw that out there in case the test ends up having something like that. But here's what's going to happen here. We're going to simplify. Assume all variables are positive. So notice we're not even doing all of that other stuff anyway. So don't worry about absolute values for this as I walk through it. Okay, let's do the first one here. Now, I said I would spell it out for you for this very first one. This will be a little more time consuming, so bear with me. Number 1, the cube root of 2000, x to the 9th, y to the 5th. I'm going to write this as the cube root of, and I'm going to go ahead and start splitting this up a little bit. I want to break up, first of all, I don't know what the cube root of 2000 is. But I have to search for a perfect cube that I do know. One that I happen to know is the cube root of 1000. That number's 10. So I'm going to break this up into 1000 times 2. Then I'm going to break this up into other perfect cubes that I can do, like x cubed, and x cubed. Notice how this is x to the 3 plus 3 plus 3 power, which is x to the 9th. Then I can do y cubed, and then all that's left there is y squared. Okay. Identify your perfect cubes so you can pull them out. This one, these three, and this one right here. When I pull them out, this will be the cube root of 1000 is 10. The cube root of x cubed is x. The cube root of x cubed is x. The cube root of x cubed is x. Cube root of y cubed is y. And then you're left with the inside right here. This is times the cube root of 2. What's left? Y squared. Okay? So your final result becomes 10 x cubed y times the cube root of 2y squared. Bada boom, bada beam. Is that simplified? Well, apparently it is. There's your final answer. Okay, so now I'm not going to do it as obviously as that. I'll show you a different way that you can write this if you'd like. Here's the 4th root. The 4th root of 81. Oh, the 4th root of 81 actually happens to be 3. In fact, here's what I'll do this time. I'll show you a different way. I can do the 4th root of each of these individually. 4th root of 81 times the 4th root of x to the 8th times the 4th root of y to the 8th times the 4th root of z to the 20th. Okay, let me try the thinner pen for a second. Maybe you'll like this more. The fourth root of 81 is 3. Yeah, I like that one more. The fourth root of x to the eighth, let's go ahead and dig that out in a different way. I said I'd do that. This can be the fourth root of x to the fourth quantity squared. Notice how I'm using that property now. There will be 2 x to the fourths that I'm taking out. Okay? You know what? Actually, here. I'm going to write that the other way. I'll do the fourth root of x squared raised to the fourth power. There we go. That way, you know this cancels out and this is all that's left. I like that way more. And I'll do the same thing for y times the fourth root of y squared raised to the fourth power. And then times the fourth root of how many z's are raised to the fourth power. That's z to the fifth. There we go. Just like that. Perfect. So that'll be, and I should have probably written this one for 3 this way so you'll know exactly what I was doing for all these. This is 3 to the fourth, like that. So all these will cancel. Boom, 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 boom. Just like that. So this will be 3 x squared, y squared, z to the fifth. See how those canceled? That one's kind of nice, how you can do that. Okay, number 3. Now I need some room, so I'm actually going to erase over here. Sorry about that. Number 3, 75 x to the square root of 75x to the fifth, y to the ninth, z to the fourth. I'm going to show you 1/3 way to do this, and this will probably be your preferred way. But let me do some introduction to it before I do. When you do 5, notice how this is square root. When you do 5 divided by 2, just in general, that's 2.5. But if you do it with a remainder, that's 2, remainder 1. When you do 9 divided by 2, that's 4, remainder 1. And when you do 4 divided by 2, that is 2, remainder 0. What's going to happen when you do these things? When I take the square root of x to the fifth, okay, I'm going to go ahead and tell you the answer to that one right now. That is x squared root x. When I take the square root of y to the ninth, that is y to the fourth root y. And when I take the square root of z to the fourth, that is z squared. There is no root z inside there. But if I had to put one, this is root z to the 0 power. Just like this is y to the first power, and this is x to the first power. Can you notice what happens here? When I did 5 over 2, that was 2 remainder 1. Look where that 2 ended up. That 2 is the same as this 2 right here. This 1 is the same as this 1 right here. This 4 is the same as this 4 right here. This 1 is the same as this 1 right here. And this 2 is the same as this 2 right here. And this 0 is the same as this 0 right here. What happens when you do this stuff? If you remember, this is x to the, the square root of x to the fifth is also x to the 5 halves power. So what happens here is you end up pulling out as many perfect squares as you can divide. 5 divided by 2 is 2. This is how many perfect squares you'll pull out for x. Remainder 1. This is how many gets left inside because you can't get perfect squares out of it. Same with these guys over here. So when I do this division, I'm going to go ahead and restart this whole problem now. So maybe it'll make sense as I explain it. Doing the actual problem here. And I promise I'll speed up all the other ones as we do this. Square root of 75, I'll leave B for a second. We'll take care of that in a bit. Square root of x to the fifth, square root of y to the ninth, square root of z to the fourth. Remember, these are all square roots, so that's a 2 outside there. 5 divided by 2 with remainder is 2 remainder 1. 9 divided by 2 is 4 remainder 1. And 4 divided by 2 is just 2. No remainder. Okay, root 75 here is, you can do root 25 and root 3. Believe it or not, one of you students are actually texting me right now. I wonder if I should actually... they're asking if I'd provide a study guide or packet for the final. I'm going to text yes. Sorry about that. Yay, I still get texts from you guys. Okay, here's what I'm going to do. The square root of 25 is 5. So what I'm going to do now, I wrote this in a different order here. Take all of your perfect squares and write them together next to each other. Okay, so this will be 5x squared y to the fourth z squared. And all my radicals I'm going to put under one hat, under one square root hat. So this is square root of 3x y, like that. And that's how those guys combine, right there. Okay, so those are those three. And I, like I said, I promised I'd speed up through all the other ones. So those three are good practice for you. Give yourself a gold or a black star, I guess. Okay, here we go. Square root of 18a to the 7th over b to the 8th c squared. Now the thing about this one, if you remember this property here, is this is one big square root. If you need to, and which is advised, because there's nothing to be doing anything for, hang on, I'm getting another text. We'll be also getting a review for the test on, yep. Doing video, haha, your smile, you are interactive right now. Doing video now, and a smiley face. I know you can't see what I'm saying. Okay, here we go. Square root of 18a to the 7th over this. I'm going to split this up into two different square roots like that. Okay, that way I know I can take the square root of the top and the square root of the bottom. In fact, what you might want to do is start splitting these guys up as well. Square root of 18, square root of a to the 7th. Square root of b to the 8th, square root of c squared. Because then you can pay attention to each individual thing. Square root of 18 is 3 root 2. Square root of a to the 7th, 7 divided by 2, is 3 remainder 1. Okay? 8 divided by 2 is 4. 2 divided by 2 is 1. Remember, no absolute value. We're not doing that for these ones. Okay? Okay, that texter just called me da bomb. I appreciate that. I really do. Put these together on top. That's 3a cubed times the square root of 2a over b to the 4th times c. Taken care of. Good to go. Okay, this one, same thing with the products. If you want, you can join these all as one thing first. That way you're not splitting things up and then, oh, you have to morph them again and then maybe do some more things with that as well. So I'm going to make this one big square root hat. I'm going to do 4 times 12, which is 48. I'm going to do a to the 5th times a, which is a to the 6th, and b times b to the 4th, which is b to the 5th. Square root of 48, I can do 24. Let's see here. 4 can come out of that. 2 root 12 and another 4. Oh, 16. 4 root 3. 6 divided by 2 is 3. 5 divided by 2 is 2 remainder 1. 4a cubed b squared root 3b. Notice how I join the rational values and I join the irrational values together. Let's use a different color for the sake of stuff. Okay, cube root. Let's just be careful with that. Now notice how there's reason to sometimes blend things together and sometimes not. This time I'm going to split these up again. Cube root of 54, especially because we haven't talked too much about cube root yet, times cube root of x cubed times cube root of y to the 10th. Cube root of 54, okay, that's not a perfect cube, and you might be saying, well, how do you do that without a calculator? One thing you'll have to do a little bit is know some of your perfect cubes. So let me write some down here. 1 cubed is 1, not that you need that one. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. I'm going to stop right there. Find factors of 54 where you can find a perfect cube if possible. Sometimes it won't be. In this case, 27. I can do cube root of 2 times the cube root of 27. Cube root of x cubed is x. 3 divided by 3 is 1, remainder 0. 10 divided by 3 is 3, remainder 1. Okay, cube root of 27 is 3, so at the end I'll have 3xy cubed. Oh, I'm sorry, this is a cube root right there as well. So this is kind of weird. 3xy cubed times the cube root of 2y, like that. I guess that's number 6, so I'm going to move on to number 7. Number 7, okay, simplify, assume all variables. Okay, same instructions. We're going to multiply and FOIL, no biggie. First, 2 times 5, that's 10. 2 times negative root 5 is minus 2 root 5. Root 5 times 5 is positive 5 root 5. And root 5 times negative root 5 is negative 5. You can now combine like terms here. 10 minus 5 is 5. Negative 2 root 5 plus 5 root 5 is negative 2 plus 5, which is 3 root 5. Okay, this one, when you add these things together, they have to be alike. So for instance, I need to have the same multiple here and here. These are not the same. But I can maybe make them the same, so that's the purpose of this. I need to take the cube root of 16 and see what I can do with that before I start playing with anything else. Remember what we did here. Find perfect cubes. Hey, 8's a perfect cube. I can split up 16 into the cube root of 8 times the cube root of 2. Which the cube root of 8 is 2, so this is 2 times the cube root of 2. So this will be, this whole thing is 8 times 2 times the cube root of 2, which is 16 times the cube root of 2. Plus 2 times the cube root of 2. 16 plus 2 is 18, so you get 18 times the cube root of 2, like that. Okay, number 9. The way you simplify this one, remember one of my rules, or well, not my rules, but math rules. You cannot have a radical in the denominator, period. So I actually need to rewrite this because I don't have enough room. The way to go about this here is you need to find, well, here, I'm going to start by writing this. Check out over here, a plus b times a minus b is a squared minus b squared. Notice how perfect squares absolutely come out of here, and any inside fluff gets canceled out. On that same token, a plus root b times a minus root b becomes a squared minus square root of b squared, which is b. Notice, irrational numbers go out of the way. That's when you multiply this guy by its conjugate form over here. So if I multiply top and bottom, you have to do top and bottom because it's a fraction. We're simplifying. We're just multiplying by 1. I'm going to multiply top and bottom by 1 minus root 3 over 1 minus root 3. That way, on the bottom, this will become perfect square minus perfect square and all that jazz. Now the top will have an irrational number because, well, hey, this is an irrational number. There's nothing wrong with the numerator having irrational numbers, just the denominator. And it's just because when you have a fraction here, you want to figure out what your whole thing is out of that you're comparing to. It's just a nice thing to do. So doing the top, this is distribution. Make sure you multiply the 4 by both values. That's 4 times 1, which is 4, and that's minus 4 root 3. Now this will be over. I can write it out for you if you'd like. This will be 1. 1 times 1 is 1. 1 times negative root 3 is negative root 3. 1 times positive root 3 is positive root 3. And root 3 times negative root 3 is negative 3. So here's what gets to happen. You're like, well, wait, there are still irrational numbers down there. Negative root 3 plus root 3 is 0. Those go away. You're just left with 1 minus 3. You've achieved your goal. We still need to finish the problem, but you've done the part that requires you to, get rid of the radical in the denominator. So we have 4 minus 4 root 3 on top, 1 minus 3, which is negative 2 on bottom. You're not yet done, and in fact, this was one of the other simplification rules that I said. I said, make sure you pay attention to number 9. Don't have negatives in your denominator. It's rude. One of your other things. Compare it to a positive whole. Divide this term by negative 2 and this term by negative 2, and you will get negative 2 plus 2 root 3. You can either write it that way, or you can write it as 2 root 3 minus 2. So either of these are accepted. Sometimes, another simplification rule, maybe you have negatives, maybe you have positives first, just because. Doesn't matter. But both of these are the same thing. Okay, number 10, you have a radical outside of this guy. We're just going to multiply these in. No biggie. But the question is, do you want to get a big number, take the square root of the big number, or do you want to work with something smaller? It's up to you. I'll show you a different way other than just doing 24 times 6 and trying to break that down. Let's look at this differently. Let's try and, you know how the square root of two numbers that are the same just become that, or whatever? What if I broke apart this? So this will be square root of 24 times square root of 6 minus the square root of 24 times square root of 8. What if I broke apart 24 into a factor of 6 and 4? So the square root of 4 times the square root of 6, that's 24, times the square root of 6 again, because that one. And what if I chose this 24 and broke it apart in terms of 8? Root 3 times root 8, that's 24, root 24. Then times this root 8 right here. Well, the square root of 4 is 2. The square root of 6 times the square root of 6, I don't have to break it apart any. That's 6 right there. So I've already done myself a service breaking it apart into something where I could go straight into it just like that. Square root of 3, I can't do anything about that. Shame. Square root of 8 times the square root of 8, though, is 8. So 2 times 6 is 12, and this is minus 8 root 3. I didn't have to go into 24 times 6, do that big multiplication, and then take that number, which, by the way, would have been square root of 144. That's not bad. This one, square root of 24 times square root of 8, might have been bad, though. Notice how it didn't come out to a perfect square. So, when in doubt, try some different things. This is an example of something else you can try. Okay, number 11. I'm going to go ahead and join these guys all together, but I'll do each individual thing, like I'll combine the constants together, then the x's, then the y's, then the z's. So I'll do cube root of 50 times cube root of x to the 10th, it looks like, times cube root, pardon the messy handwriting, it's really tough on this doodle pad, cube root of y to the 4th times cube root of z to the 6th. Remember, we divide by 3 with exponents here. This one I can't do anything about. Cube root of 50, unless you can think of something, I can't break that down. It looks like that's going to be a part of your radical. Okay, for the x's, 10 divided by 3 is 3 remainder 1. 4 divided by 3 is 1 remainder 1. And 6 divided by 3 is 2. And then you have that cube root of 50 also hanging out here. Okay, x cubed y z squared sits on the outside. And then on the inside sits a cube root of 50 x y. Whoops. There we go. Glad you could follow along there. And as always, run out of room on the right side here. Let's see if I can squeeze it in. I can always write underneath it. That's cool. Okay, this is an example where you might want to actually join these two as one big square root, and I'll kind of show you why. Because everything, well, versus, here, let's check this out. Take a look at, see this problem right here? You notice how we split the big one into two little ones? The reason was because there was nothing to cancel on top and bottom. And in fact, there were things to do in here, taking square roots of them. On this one, you can choose to take square roots on top and bottom first if you'd like. There's no problem with that. But the reality is, I can do 24 divided by 6. I can do a to the 6th divided by a to the 7th and cancel things out. And I can do b to the 5th divided by b and cancel things out. And leave it all under one square root. So my next step, 24 divided by 6, is 4. That's still under the square root, mind you. A to the 6th divided by a to the 7th, that's going to give you an a on the bottom. If you think about me using another property here, a to the 6th divided by a to the 7th is a to the 6 minus 7 power, which is a to the negative first power, which is 1 over a. That's why the a stays in the denominator, and because there's one more multiple of a down there than there is up here. B to the 5th over b is b to the 4th power. Now this is still all under one square root. As I did that, maybe now it's time to go ahead and say, okay, nothing else to cancel. Now I can put these under different square roots. Square root of 4 times square root of b to the 4th over square root of a. Square root of 4 is 2. Square root of 4 is 2. Square root of b to the 4th is b squared, and you have square root of a down there. Don't think that you're done though, because you have to remember you have to have a rational value in your denominator. So we have to multiply by the square root of a over the square root of a. That will rationalize our denominator right here. That will give us a value of a on bottom, as we wanted, and 2b squared root a on top. There you go. That is a simplified version. It doesn't look as clean as this, but it's simplified. That's the math idea of simplified, and they also want you to say every so often there is something you can cancel out down there when you do this. It's worth it. Number 13. I'm going to do the same thing as I did last time for the very reason that I can do 108 divided by 3, and I can do a to the fourth divided by a. And there's a b cubed. 108 divided by 3 is 36. A to the fourth divided by a is a cubed. B and b cubed is still up there. Okay, square root of 36 is 6. 3 divided by 2 is 1, remainder 1. And 3 divided by 2 is 1, remainder 1. So this gives you 6ab root ab. Kind of interesting. That's a 6. Okay, once again, I do feel good need to want to do this the same way that I did the other ones. Make it one massive cube root. And you don't have to do the massive cube root. The fact is, people perceive things a little better if you see this on the inside like that. You can do cube root of 24 divided by cube root of 3 and make that the cube root of 8 on your own. That's fine. There's no problem with that. But looking at it like this, I think everyone can agree. I see 24 over 3 much easily here. I see a to the fifth over a squared much easily here. This becomes the cube root. Like I said, cube root of 8. A to the fifth divided by a squared is a cubed. Okay, the cube root of 8 times the cube root of a cubed. That gives you 2a. Boom. Finally, this is an example where you can choose to do whatever you need to. I think I can do 27 divided by 216. If you can't, maybe trust that comes out to a good number. If not, this might be the ones where you wish you had a calculator. You do know, and here's just a number talk for you. I know, because this is what I had to do when I did this problem. I know that 27 times 10 is 270. And I start to work backwards. Or I work from 216. And I say, can I get to 270 by adding 27 here? 243, 270, yes. This must be 27 times 8. That's a little thing for you in case you haven't been doing too much without calculators before in the past. That's a mental math idea. So this number reduces to 1 over 8. So this is the cube root. Oh, you know what? I will split this up afterwards. But this is the cube root of 1 over 8 times x to the 8th z to the 5th over y to the 6th. This might be a good time where you do separate this in cube roots on top and cube roots on bottom. So this becomes the cube root of x to the 8th times the cube root of z to the 5th over the cube root of 8 times the cube root of y to the 6th. 8 divided by 3 is 2, remainder 2. Hang on, I need some more room for this one. I'm going to do it down here. And in a different color. I've been using too much black on that one. Okay, the cube root of 8, again, it's 2, remainder 2. Cube root, or 5 divided by 3 is 1, remainder 2. Okay. Cube root of 8 is 2. Cube root of y to the 6th, 6 divided by 3, is 2. So your final answer then is x squared z, right there, times the cube root of x squared z squared all over 2y. These are big numbers. I mean, big answers. They don't get so clean, but that's more simple than the original one was. Not that it looks simpler, but trust me, it is. Okay, simplify. Assume all variables are positive. Leave all exponents positive. Here's where we got to do some distribution. If you remember this property here, I'm going to distribute my exponents into individual components. Now, you have to distribute into every term that's being multiplied inside here, including the negative 32. That's something you cannot forget and you would like to not forget. First step I'll do is just go ahead and rewrite that so I've distributed first. Negative 32 to the 1/5 times y to the 15th to the 1/5. Now we take the other property. Well, negative 32 to the 1/5, I'm going to go ahead and write this here, is the 5th root of negative 32. Some people like seeing that more. I'm going to use this other property here, and power raised to the power means you multiply these two. This is y to the 15 times 1/5 power. Fifth root of negative 32 is negative 2. 15 times 1/5 is 3, so this is y cubed. There's your final answer. Okay, negative 12. Now people can do this two different ways. I'm not going to do both. I'll just go ahead and do one. I'm going to just distribute this in. I did say when in doubt, make things positive first, like the exponent, but then you're dealing with fractions within fractions to start with, and I'd rather deal with other stuff that I can first. Distribute the negative 12 into the x to the 2/3. So that's x to the 2/3 to the negative 12 power times y to the negative 1/6 to the negative 12 power. Remember, these get multiplied. I'll just go ahead and save you time and do the multiplication for you. Negative 12 times 2 is negative 24. Negative 24 divided by 3 is negative 8. That's x to the negative 8th power. And negative 12 times negative 1 is positive 12. 12 divided by 6 is 2. So that's y squared. You're not done because you cannot have negative exponents. X to the negative 8th is now 1 over x to the 8th. So this becomes y squared over x to the 8th power. Like that. 1 over x to the 8th times y squared becomes that. And you can see the other good reason why I didn't put the negative thing there first is because this had a negative here, which means this negative in the denominator would have had to go up to the numerator anyway. That would have been a wasted step and more stuff to write. Okay, y to the 1/2 power times y to the 3/10 power. Same base, you have to add the exponents now. That's y to the 1/2 plus 3/10 power. 1/2 plus 3/10, some other stuff here. You got to do common denominator, of course. 5/10 plus 3/10, which is y to the 8th tenths. It would be nice if you could reduce a fraction from this point. Don't stop there. That's y to the 4/5 power. If you also want to, you can do y to the 4th and then the 5th root of that. If you want to write it that way, if they said write it in radical form, that's what you do. These are both the same thing. They're both appropriate answers unless they say specifically write in exponential form or radical form. Okay, I'd say this is more appropriate, personally. And I normally do things in that vein anyway. Like right here. This whole thing is raised to the 1/2 power. So you can either take the 1/2 and do all that, or do what I'd like to do and say, I don't like looking at fractional exponents when there's a better thing that I can write, such as the square root. This is the same thing as the square root of all of this. Now, some people have different preferences. When I know a square root exists, I like writing square root. We've done problems like this already. I will save you time here and help you out. You do the square root of literally everything. We're going to do the square root of 16, that's 4. The square root of x to the 14th, you divide by 2, that's 7. The square root of 81 is 9. The square root of y to the 18th, 18 divided by 2 is 9. There you go. I said I'd speed up when you come into more things like that. Okay, so we are done with the expression stuff, simplifying those. I'm going to go into solving radical equations. So I'm going to give you some more notes here. Check it out. Okay, when a radical appears in an equation like this, or a fractional exponent, by the way, we're going to look at both of them. You cancel it out, like this thing, to solve for x by raising it to a power that will give your quantity a degree of 1. What that means is, if you think about the square root of x, that's also the same thing as x to the 1/2 power. Okay, that degree is not 1, the degree is 1/2. That's a problem. We need to find x to the first power. Well, whenever we did x squared, we took the square root of it to make that happen. So whenever you have the square root of x, you square it to make it happen. Let's square both sides. To confirm that notion, let's go ahead and do that over here. Let's square x to the 1/2. That becomes x to the 1/2 times 2 power. 2 over 2 is 1. You get x to the first power. This thing agrees with this thing right here. So you'll get x equals 4 squared, which is 16. Now notice, this is the same problem technically. If you subtract 2 from both sides, you'll get square root of x equals 4. So this is the same problem. What you don't want in this problem, though, is to automatically square things when your radical is not by itself. The radical must be isolated on one side of the equation, otherwise the radical will not clear out. Let's take, for example, what if I tried to square this immediately when this problem looked like this? Squaring means square both sides, like that, and that means this is square root of x plus 2 times the square root of x plus 2. And this equals 36 on this side. Okay, all good and fun. But, okay, square root of x times square root of x is x. Then you get, 2 root x. Will it cancel out here? No. Another 2 root x. Then plus 4. And then you get x plus 4 root x plus 4 equals 36. I did nothing to help solve my equation any better. In fact, I made it worse. Now I'd have to move everything else over. The key is to isolate your radicals. When you have information on the side where your radical is and you square it, you don't clear out your radical. It doesn't help you. So you would have to do what I just talked about before. Subtract the 2 and you'll get square root of x equals 4. Then you can square it. Then it clears out just like we did right here. And you get a prime example of what you can do. So let's go ahead and try to solve some radical equations here. Oh, I'm sorry. I'm going to talk about some more stuff here. The next step, right here, extraneous solutions. Ignore the graph stuff for now. I'll tell you about it in a second. Extraneous solutions appear when an unwanted solution results from raising both sides of your equation to an even power. So, I'll give you an example of what I'm talking about through use of graphs here. By extraneous means you got an answer and it doesn't work for your original equation. And there are reasons behind that for square roots and everything else. So let's go back to here. And let's take a look at, we had to square this guy in order to solve for it. Okay, I'm going to show you examples of values where what happens to when you square sides and you get more than the amount of solutions that you expected to get. This is because an even power converts real number quantities to positive values and new results can come about that are invalid in your original equation. I won't take too much time explaining that. I explained it in class, and I want to get through all these for you. These are two graphs, and you can trust these graphs. I went online when I graphed them. Y equals the square root of x minus 3 is this blue one right here. Y equals x minus 5 is this red one right here. Notice how they only cross at one point, which means this is their only solution. That solution is actually 7, 2. But the x value, if you wanted to solve for x in this equation, you would square both sides, and you would get x minus 3 equals x minus 5 quantity squared. If you wanted to keep solving for x, you could. You could keep going. But let me just show you it through graphs, because we're going to do actual problems. Let's graph y equals x minus 3 and y equals x minus 5 quantity squared. X minus 3 is in blue. X minus 5 quantity squared is in red. Look what happens this time when we squared it. We got 2 solutions instead of just 1. We got x equals 7, like we should have last time. And here we also got x equals 4. Well, in the original equation, this one right here, technically in this original system, there was only one solution, just x equals 7. How come this one got 2? It happened when you squared it. And really, I'll do a brief explanation. The reason is because when I go from this step to this step right here, and I square this set like that, this could have been positive root x minus 3. This also could have been negative root x minus 3. Tell me that I'm wrong. Negative root x minus 3. Tell me that I'm wrong in that if I square negative root x minus 3 squared, I don't get this number. The answer is, oh yeah, you know what, you do. Here's the and here's kind of all that's happening here. And I'm going to erase this and I'm going to move on. All that's happening here is, what if I included square root or negative square root of x minus 3? Check out the green graph right there. Where does it intersect? At x equals 4. That's where that other solution comes into play. The problem is, this isn't our graph. The green is not our graph because the green's not our equation. Because this equation wasn't a part of this original equation. And notice, no matter what happens when I square this guy here, I'll still get x minus 3 when I square positive root x minus 3 and negative root x minus 3. Either of these that I square will get it. But this was not my equation. This one is extraneous. It is not a part of the original equation. So what you're going to have to do when you solve these things, and I'm going to do it with you right now, is you're going to have to double check and make sure that you didn't solve for an extraneous solution that should not have ever been there. Let's do it. Number 24. The square root of 3x plus 7 equals x minus 1. Okay, step 1, isolate your radical. Done. My radical is by itself. Now I have to square both sides. Let's go and solve for x. 3x plus 7 equals x minus 1 squared is x squared minus 2x plus 1. Ooh, quadratics. We've done these before. Subtract 3x. Subtract 7. X squared minus 5x minus 8 equals 0. Oh, I'm sorry, not minus 8, minus 6. I can't do math. X squared minus 5x minus 6 equals 0. This factors to x minus, help me out here, x minus 6 times x plus 1 equals 0. Therefore, x equals 6 and negative 1. Done? No. Check for extraneous solutions. And what that means is I'm going to rewrite the original equation down here. I'm going to plug in both values and see if any of them do not work. One of them should work. One of them should absolutely be plugging in. Well, actually, I don't know if absolutely is true. One of them hopefully would be plugging into here. The other one may or may not. Try 6. 3 times 6 is 18. 18 plus 7 is 25. Square root of 25 equals 6 minus 1. 5 equals 5. 6 checks out. Let's try negative 1. 3 times negative 1 is negative 3. Negative 3 plus 7 is 4. Square root of 4 is negative 1 minus 1. Square root of 2 equals negative 2. No, it does not. So what happened? I want you to keep in mind the thing that I talked about before here. It assumes that you were looking at plus or minus your number. Because when we squared it, it didn't matter. It became positive 3x plus 7. It didn't matter if it was positive 3x plus 7 or negative 3x plus 7. In this case, we only had positive 3x plus 7. If we looked at negative 3x plus 7, look what would have happened. This would have been negative root 25 and negative 5 equals 5. That one wouldn't have worked. But this one would have. Negative 4, square root of 4, is negative 2. This one would have worked. So the thing is, we're not looking at the plus or minus version. We're only either looking at one or the other. So you have to make sure which one works, which one doesn't. Now in this case, 6 worked, negative 1 didn't. Negative 1 is not an answer, 6 is. X equals 6 is your only solution to this original equation, despite the fact that you solved for something down here. Because remember, this made up for a quadratic that really wasn't there in the first place. Okay, here's an example of doing one where you don't have, it's not just square root. You are doing a little more than that. This is to the 2/3 power. Now remember, we need to raise it to a number that will give us to the first power. So you can either do this in 2 steps or 1. I'll do it in 2 steps first to show you what it's like. And then the next time I'll do it just in 1 step. If this is over 3 like that, what if I just raise it to the 3rd power? You know what? I'm going to take the square root first, actually. What if I took the square root first? Raised it to the 1/2 power, so to speak. That'll cancel out this 2, right? This will now be 3 plus 2x to the 1/3 equals square root of minus 3. Now, one thing you don't want to forget here is we did take the square root of that side, which means we are considering that when we squared this number, it would have been positive, which means this could have been positive or negative, which means we have to look at the positive and negative version of this. Now, when we cube this guy right here, let's go and raise this to the 3rd power, like that, raise this to the 3rd power, this is 3 plus 2x equals plus or minus 27. Remember, it is plus or minus. You cube a number, the negative becomes the negative. At this point, I like to split this up into two equations when you're dealing with the plus and minus. I have 3 plus 2x equals positive 27, and 3 plus 2x, 3 plus 2x equals negative 27. So this is 2x equals 24, and x equals 12. And this is 2x equals negative 30, and x equals negative 32. Whoops. I just subtracted. X equals negative 15. Good to go right there. Check for extraneous solutions. You know what? This isn't an extraneous solution problem. The times when they occur are when you're dealing with your radical, and then you're dealing with a linear x value that sits on the outside, because what happens is this becomes a quadratic, and it tends to do something that you wouldn't want it to do. It bounces back up because it has a vertex. Square root functions don't really, we call it I call it a vertex, but it doesn't really do this part. It only does half of one, so it only hits at one point. It doesn't hit at that second point like you can imagine there if there's the negative version of it. So the extraneous solutions appear when you're looking at an x sitting on the outside, not having to do with the same root that this other guy's in. We can still double check. Let's check this negative 15. 3 minus 30 is negative 27. The cube root of negative 27 is negative 3. Negative 3 squared is positive 9. That's why we have to consider the plus and minus version of this thing, because when you square the number, it becomes positive. Unlike this one where we're doing the cube root, so whatever sign we have to consider that that's the one we're doing. So I'll show you the one-step method this time that we do this. And I'm actually going to erase some work over here. I want to get some room. Okay, before I do any of that, isolate your exponent. Before I said radical, I really mean any exponent. I have to add 5 to both sides first. Now I have to divide by 2. Okay, this 2 has nothing to do with this 3/4. It's not associated with it. Just this quantity is. So divided by 2, I have x plus 1 to the 3/4 equals 27. Okay, here's the one-step method. When you raise it, notice how what I did before was I took the square root and then I cubed it. Taking the square root was kind of like raising to the 1/2 power. Well, it is raising to the 1/2 power. So this was really raising it to the 1/2, and then I raised it to the 1/3. That's raising it to the 3/2 power. Notice that 3/2 is the reciprocal of 2/3. So what I'm going to do in this one is I'm going to raise it to the 4/3 power, because that's the reciprocal of 3/4. And I have to do the same on both sides. Because this will be 3/4 times 4/3. 3 over 3 is 1. 4 over 4 is 1. We get x plus 1. Now, take the cube root first. That's 4/3. Cube root of 27 is 3. 3 to the 4th is 3 times 3 is 9, times 3 is 27, times 3 is 81. It's not plus or minus 81. There was nothing we did there to warrant that. It's just 81. Subtract 1, x equals 80. And you can always double check these numbers in the original equation. Make sure they work. Number 27, the 4th root of y minus 3 minus 2 equals 0. I know what you're thinking, raise to the 4th power. You do want to do that. Just make sure you isolate your radical first. Add 2 to both sides. Okay. Now we can raise it to the 4th power, and we won't deal with the hassle of not clearing out radicals that needed to be cleared out. We also don't have to deal with foiling 4 different quantities. That would be terrible, especially with radicals. This is y minus 3. 2 to the 4th is 16. So add 3, y equals 19. Number 28, subtract 3 to start with. Get rid of that guy. Or not get rid of it, just move it over. Okay. What did I say before about that one-step process? Raise it to the reciprocal of your other guy right here. So I'll go ahead and do that. to the 2/3 power. So 8 also goes to the 2/3 power. Okay, so this becomes 6 minus x to the first power, which is what we want. Cube root of 8 is 2. Notice how these come out great for you. 2 squared is 4. I could have done 8 squared, which is 64. That's not too big. And the cube root of 64 is 4. That still gets us there. Subtract 6 and divide by -1, multiply by -1. You get x equals 2. And there's a final answer. Got 2 more for you before we do our final thing in graphing. X minus 4 equals square root of x minus 2. Square both sides. Boom. Now this is an example of one where you want to check for extraneous solutions. Again, before I keep going. The reason is because of this x sitting on the outside right there. This thing's going to get squared. It's going to create a parabola like on those graphs. It's going to cause some results that's different from what the other ones were. So, x minus 4 quantity squared is x squared minus 8x plus 16. And this becomes x minus 2 over here. Okay. Subtract x, add 2. Okay. And this is x minus 6 and x minus 3 equals 0. So x equals 6 and 3. Now, check for extraneous solutions. Let's try 6 in the original equation. Let me erase these guys here and say it out loud for you. 6 minus 4 is 2. Let's use colors here. 6 minus 4 is 2. 6 minus 2 is 4. Square root of 4 is 2. 6 checks out. Let's try 3. 3 minus 4 is -1. 3 minus 2 is 1. Square root of 1 is 1. -1 does not equal 1. This one does not work. You know when it would work? If this was the negative version of that, that would have given you -1, but it wasn't the negative version. It doesn't give you that. This is extraneous. You can keep it there, actually. You don't have to cross it out. You can keep it there. Just say, do something to indicate this is not a solution. It is extraneous. Do not keep it as a solution. Like I said, you can do that, but nothing else. Okay, here we go. What do you think we should do? I say divide by 3. Get that smaller number there. This is 27. Okay. Raise this to the... Let's see how much you know about this now. I want you to try it. What do you think? Yep, 4/3 power. I feel like I'm playing Blue's Clues. Okay, x plus 3 equals... Cube root of 27 is 3. 3 to the 4th power is 81. We've kind of already had a number like this. And x equals 78. Okay, that's it for solving. Graphing square root functions. Bum, bum, bum. Parabola. Vertex form for a parabola looks like this. Let's get you familiar with it. Okay, x minus h squared plus k, where hk was your vertex and a was your stretch factor. Now, your stretch factor is always vertical. You multiply, you plug in an x value, you end up multiplying this by something, your y value gets affected. So if this is 2, your y value gets doubled. If it's, you know, something like that. Okay. Now, the only difference here with this thing, besides the square root, is this b. This is something that I've kind of created with my own invention. Ever to be a positive 1 right here. Make this an A. Make this a 1. Can absolutely be your vertex with K, and so on and so forth. To put it into vertex form and know which way the graph goes, and talk about times x plus 2 and square root minus 4. Some people might say, all right, vertex is -2, comma -4. That's nice. That's not wrong. Let's do domain first, though. As far as graphs, this is a real number Cartesian coordinate plane. This doesn't have imaginary numbers. So as far as domain goes here, we have to understand that the inside thing right here must be 0 or positive. So I can write a domain that x plus 2 has to be greater than or equal to 0. So x has to be greater than or equal to negative 2. Now, if x is greater than or equal to negative 2, notice that your square root graphs, they all look like this. They look like that, or like that, or like that, or whatever. Your domain is the start of that point, right there, there, or there. Which also means that your range is set at the same place where your x value is. So to find the range, you plug in your minimum or your maximum domain value into your original equation, and you can find the other part for your range. Or you can graph it first. It doesn't matter. But if I do it this way, which is the only time I'm going to... No, that's not true. I might do it this way again. To find the range here, I could plug in negative 2 for x in the original equation. Y equals negative 3 times negative 2 plus 2, or square root of negative 2 plus 2 minus 4. Negative 2 plus 2 is 0. In fact, that should always happen there. Negative 3 times 0 is 0. Y equals negative 4. And the question now here really is that, that's not your range. That's your vertex point. But which way does it go? Does it go up or down? That's based on your stretch factor. This is negative, so this is going to be y is less than or equal to negative 4. That's the long way of figuring out. So, your vertex is negative 2, negative 4 right there. Your stretch factor is negative 3. So if you remember how we did things with parabolas, we'd go over 1, up 1, over 2, up 4. Square roots are the exact opposite of squaring. Over 1, up 1, that's the same. But instead of over 2, up 4, it's going to be over 4, up 2. So I'm going to quickly show you this here. If I graph this like a parabola, it would be 1, 1, 2, 4, 3, 9, 4, 16, etc. Your graph would start looking like that, and obviously the other side. Parabola, square roots are the other way. 1, 1, 4, 2, 9, 3. Like that. Aha. So that's what your graph would look like. Not this graph, though, because there's a stretch factor of negative 3. But this is the example. You do 1, 1, 4, 2, etc. Now this time I'm going to do 1, instead of 1, I'm going to multiply 1 by negative 3. 1 down 3. Instead of going 4, 2, I'm going to do 4, 2 times negative. It kind of falls off the map over there. That's okay. I can still sort of graph that. That's what your graph would look like in essence. Now, does that fit with your domain and range that you did? Yes, it does. Here's negative 2 and greater than for x, range. Here's negative 4 and less than for y. So the fact is, you can graph it first and then figure out your domain and range, which is what I'm going to do for range for this one. I still want to figure out the domain for this one, though, because I need to put it in proper vertex form. So this one's not in proper vertex form because I need to get positive 1x inside the square root. So what I'm going to do here is factor out the 4. And I'll have x minus 2 plus 2. This becomes, check this out, this is the square root of 4 times the square root of x minus 2. The square root of 4 is 2. So this becomes y equals 2 times the square root of x minus 2 plus 2. This is proper vertex form for your guy right here. So you already know now that your vertex is 2, 2. It wasn't going to be 8, 2. To confirm it, let me show you domain again one more time doing the thing I did last time. This inside value must be 0 or greater than. So 4x minus 8 has to be greater than or equal to 0. 4x has to be greater than or equal to 8. Divide both sides by 4. X has to be greater than or equal to 2. So notice how your vertex starts with the minimum value of 2, and then it goes to the right that way. So my vertex right here, let's go and graph that. That's 2, 2 right there. It has a stretch factor, a vertical stretch factor of positive 2, so I'm going to go over 1, up 2, over 4, 1, 2, 3, 4, up 2 times 2. 1, 2, 3, 4, like that. And that's all I have room for. Let's go ahead and graph that. Good to go. Only other thing I need here besides domain is my range. And your range, I said you can get from your graph. Y is greater than or equal to 2. Or you can get it from, literally, you get it from your vertex. You say it's 2 right there, positive stretch factor, it has to go upward. Okay, this one I'll do pretty quickly here. Vertex is 4, negative 2. This is the last problem, by the way. We're done after this. 4, negative 2. Negative stretch factor. Stretch factor of negative 1 right there. I go over 1, down 1, and over 4, down 2, like that. And it goes on through. You can always use a table. It's just you need to find perfect square values to make it all happen. Your domain, x is greater than or equal to 4. Your range, y is less than or equal to negative 2. Okay, that's it and that's all. I wonder if I made good time on this. I think it was actually pretty good considering I did 33 problems and some note-taking meanwhile. So let me go back all these other previous slides. Just say, ha 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 ha, here's all the stuff that you might have had to look at. If you have any other questions, always please ask. That's always how this goes. A lot of messy handwriting, a lot of different ways you can approach problems. Talking through it always helps. Hopefully you learned some new shortcuts along the way and you learned some other stuff as we went, even including things regarding, let's go back to it, simplification. There's a lot of things you can just talk about from there. And here's where we started. Chapter 7a, half chapter practice, 33 problems. I felt like it was still a successful video. Enjoy. Oh, somebody said that I need a sign out, a sign off thing. And I have no idea what to say to sign off. Robbie, out.